The alkyl halide starting material substrate for the SN1 reaction is the reverse, this is very important, of SN2. It's the opposite. It's tertiary, better than secondary, than primary, and methyl. In fact, at methyl, it doesn't even occur. And the reason why is because of the following. So we say here, as the number of R groups on the carbon with the leaving group increases, the rate of SN1 reaction increases. The more R groups you have, the more hindered it is, the better. And the reason why is because they are these alkyl halides that are more substituted, okay? They can stabilize that carbocation. And of course, when you have a stable carbocation, then the reaction will take place faster in the transition state. So the rate of SN1 reaction corresponds to the stability of the corresponding carbocation. So this here would be your most stable. This is again tertiary, 3 carbons, because remember, that's what happens. And then this would be a methyl. And this would be the least stable. You can have, of course, other ones in the middle, like allyl. We'll talk about this when we meet next time. But where you can actually have the resonance, what they talked about here, the resonance stabilized by having a double bond nearby. But that's the observation that we have. So the more alkyl groups bonded to the positively carbon, the more stable the carbocation. And the question is why? Now, I'm not going to belabor this, but there's a theory behind it. It's called hyperconjugation. So imagine you have your carbocation here where it has an empty p orbital. This is an empty p orbital with a positive on it. And imagine, you have a nearby methyl group. So this is an adjacent methyl group. And you have a CH sigma bond right there. This is the overlap between them. That's H right here. And that's the sp3 between the H and the C. So what would happen is that the electron density, if it's paralleling that, it will be, it can actually lend electron density to that empty p orbital. And if we have more electron density, we can stabilize that positive charge. So we're going to say here, that electron density of CH sigma bond flows into the vacant right here. This is vacant. p orbital, which makes carbocation less positive and more stable. So as I said here, the delocalization of the charge through hyperconjugation stabilizes the positive. If you're lending more electrons here, that will make it again more negative. So these are the negatives here coming over. I mean, think of it that way. Of course, we don't mean, that many electrons, but the electron density, then that would actually lessen the positive charge on the carbocation. That's what it means. So that's why we need more R groups. Leaving groups the same as SN2. There's no difference. You need a good leaving group. So in this case, of course, we know that I and water is the best. These are the best leaving groups. And of course, F would be the worst leaving groups. So they would actually slow down the reaction. The effective nucleophile, very simple. All you need is a weak nucleophile. That's all you need. And that is only the solvent. That is only the solvent. And in the next video, we will take our time to discuss the solvent effect on the reaction rate.